Welcome to Energy Innovations, a regular video series that explores the latest innovations in technology, digital, regulations, products, services, finance, and business models that are impacting the energy sector. Energy Innovations interviews entrepreneurs, energy companies, capital markets, and regulators to understand how the energy industry is changing.
Welcome to Energy Innovations. On today's episode, I want to talk through a critical issue that's facing the planet in general, and that is the growing volume of methane gas that's accumulating in the atmosphere. Methane, as it turns out, is much more of a hazard to global warming than CO2. And interestingly enough, there are many sources of methane emissions on the planet that are actually under human control. And we can do things to reduce the methane volumes that are being emitted. And one of the companies that has a specialization in this very area is a company called Questor. And the CEO is Audrey Mascarenhas. And I've invited Audrey to join me today to talk through what exactly this problem is and how we might go about dealing with it. So Audrey, welcome to Energy Innovations.
Thank you, Geoffrey. It's a pleasure to be here and to get to speak on my favorite topic.
Exactly. You and I met about this, probably 2 or 3 years ago. I remember having a lunch in a restaurant, and you told me about how critical methane is, and that the world is actually, by concentrating so much on CO2, we're actually missing potentially the bigger, more solvable problem, which is methane. And that was very intriguing to me back then. It still is. So let's unpack this a little bit. Why is methane specifically more of a hazard than CO2?
So methane, actually, from a global warming perspective, has much greater impact. So over 20 years, it's 86 times worse than CO2. Many of you may have heard a 100-year global warming perspective, which is 25 times worse than CO2. What it means is when methane's first emitted into the atmosphere, those first 20 years, it is 86 times worse than CO2 in terms of absorbing heat. What that means is we get a big bang for our buck if we deal with the methane first. And so because it's so much worse, it means we can effectively, at much lower cost, reduce our global warming greenhouse gases by focusing on the methane piece.
Yeah, focusing there rather than on CO2 as an example. Yeah. And now there are a lot of sources of methane, cow belching, and rivers and things naturally emit methane. The decomposition of organic materials, widely known to be, as it erodes, releases methane to the surface. George Washington used to comment about a river in the United States that you could actually ignite. And so there's lots of examples of this. But where are the methane emissions of concern that are more man-made, that we actually have we can actually do something about?
So a lot of the man-made ones are coming from our industrial processes, right? So whether it's oil and gas, and we'll come back and talk about that, but it's agriculture. It's around what we do around waste management. So a lot of things in agriculture, as they decay or break down, release methane. Even landfills and wastewater treatment are big sources of methane. Now, the area that we focused on because of the background is really the methane coming from oil and gas. And it comes from our operations right from the time we drill a well all the way to the time that we deliver gas to our homes. And one of the struggles around this methane is that we may have underestimated it significantly, right? But we should look at that as an opportunity because it means that we could have a great impact with, and because methane is so much worse than CO2, we could have a great impact, but also truly do it in a cost-effective way.
And let's just, if we just visit for a second in a traditional oil and gas context, I've drilled an oil. I've drilled an oil well,
right?
and I've at the same time the methane is present in that oil deposit, so we have a kind of an associated gas with the oil deposit. And so now as I start lifting my product to the surface, where does the methane problem start to surface at that stage?
Okay. So it's because every barrel of oil usually has gas entrained in it. And a lot of times it's easy to handle the oil because it's a liquid. We can put it in a tank, we can put it in a truck, we can put it in a pipeline. Gas tends to be a little bit more problematic because it could have impurities like hydrogen sulfide or CO2 in it. And we've got to gather it. We may have to compress it to get it into a pipeline if we've got infrastructure close to us. If there's no infrastructure, that's when we will typically look at flaring or venting it, and it becomes a lot more problematic.
Now, are we also using methane to drive some of the mechanics of these wells? To say, because if you need energy at some wells.
Mm-hmm.
Are we also using some of this methane that's under pressure to actuate valves and to actually run the well too? Is that actually still the case?
Sometimes we do, and once again, it depends on what's in that gas. If it's very rich associated gas and it has hydrogen sulfide in it, then we won't, because sour gas will tend to corrode a lot of our equipment.
Right.
So we'll try to use it as much as we can, but usually, there's a volume that we can't use, and so that's typically where it's either flared or vented, depending on where you are. And interestingly enough, the World Bank has estimated that every day globally, we flare and vent about 14.5 billion standard cubic feet a day. And we've been doing this for the last 50 years. And it's because we don't have a lot, that'll happen in a lot of places where we don't have infrastructure. Mm. The prize and the value has always been oil. And now it's starting to change, as we have more and more of it, energy demand. And the world is really looking at natural gas as this transition fuel, right? So the price is starting to come up, but there's still a lot of capital we would have to spend, with infrastructure, with processing, with compression and pipelines to deal with the gas.
Yeah, to move it from where it originates to where there's actually a market that can consume it, and there's a cost associated with all that infrastructure. Mm-hmm. Plus, it takes energy to move it from, say, northern Alberta to a consuming market in Edmonton or Calgary, which adds costs, and that also impedes the economics. Now, you mentioned how many billion square feet or cubic feet per day?
14.5 billion standard cubic feet a day. Now, what's interesting, and so recognizing that that's a global number,
yeah,
we've done some quick calculations. If we spent $3.6 billion and made sure that volume was cleanly combusted and no methane was emitting to the atmosphere, we could reduce greenhouse gas emissions over 1 gigaton a year. In other words, 2.5 million tons a day.
That's a huge
amount. And we could do it. Yeah. So some of the work that MIT did showed that the things that we have that could have the greatest impact and stop this temperature rise, one was don't put methane into the atmosphere. Mm-hmm. And the second one was be more energy efficient with the energy that we use. Yeah. Currently, globally, we only use 40% of the energy in a barrel of oil. We waste 60% of it. So,
wasted in what way? It turns to heat as you combust it, and then the heat is just not used?
Exactly. Yeah. So engines have an efficiency. We have to use energy to process. Right. And to transport, right? So if you think about that, if we could double that 40% to 80%, for example, we would automatically reduce our emissions in half. But more importantly, we would halve the amount of oil or gas that we need.
Actually require, yeah.
Right? So in essence, we not only would we reduce emissions, but perhaps by using less, we would meet some of the goals that everyone's saying of reducing the amount of fossil fuel that we use. I don't believe it is saying we're going to shut in all of our oil and gas, because reality is one of the other things we've got to balance is clean energy for everyone. That's one of our sustainability goals. And even by 2035, 75% of our global energy need will still come from fossil fuel.
Yeah, whether we like it or not, we have to fix this. Yeah.
Yeah. So let's make sure when we produce oil and gas, we're doing it in the cleanest way possible, which more importantly than anything is don't put methane into the atmosphere. Make sure it's not leaking.
Yeah, exactly.
Right?
Yeah. Yeah. So if we tightened up the valves and the connections, the flanges, the compression assets to capture the rogue emissions and reduce those, that's a big plus. We can stop using methane as an actuator for industrial equipment where it just gets vented. But still there remains the need to consider the possible for the methane that we lack the infrastructure and we can't cost effectively move it and we can't put it back into the ground. What do we do with that? And right now the industry flares that. That's not particularly effective. Are there problems? I mean, I've read several studies that declare that flaring is not an effective answer because it doesn't appropriately destroy the other compounds that might be present in the gas. Is that accurate as a conclusion?
It is very much, right? And Geoffrey, we've been assuming that a flare is 98% efficient. So it's one of the reasons we haven't got a lot of focus on it. All of the research and the drones and the satellites are showing that we have a lot of methane leaking from flares. But in addition, because they aren't high efficiency, and especially with associated gas, which is rich, you'll often see those flares being black and smoky. So they're releasing VOCs, of volatile organic compounds, and particulates, which have a big impact on air quality and human health, but also have an impact on climate change. So that's one part of it. The other part that we're missing is the maintenance. So we know that engines, just like your car, after so many hours, need to be overhauled. And if they're attached to a compressor, we tend to blow down or vent the gas so that we can safely work on that equipment. Similarly, we pig pipelines, right? Which means we want to make sure that there's no liquid traps in it. That's the source of gas. If an engine goes down and we go to restart it, we usually do a soft start, which means we're venting. So a lot of the methane that is being picked up on satellites is actually occurring from maintenance events. So yes, we can do some things with pneumatics and vapors of tanks, but we've got to take a much bigger picture and make sure that we're also picking up far bigger sources that actually are contributing way more than we realize. And so that's one of the reasons you're seeing a lot of reports. And a new one just came out yesterday, I think it was, on New Mexico, which is showing that we've underestimated our methane emissions significantly because we haven't accounted for some of these other sources.
These other location, other mechanical issues that we face. Now, so the innovation that's of interest today is the ability or the if you like, the invention of super high efficiency combustion capability to take a stream of gas which has no commercial value, and so we struggle with what to do with it. Right. Flaring it creates all these associated issues. How does combustion? I mean, flare is a kind of combustion. So what is the extension or the elaboration of this combustion technology that is so innovative?
Okay, so Questor has developed and patented this system that allows us to guarantee 99.99% efficiency. And so our system actually creates this vortex in the chamber, which naturally brings in air, and we're able to bring in excess air. And we get a lot of mixing. We leave those molecules in our chamber for a period so that we're absolutely comfortable that we're converting every molecule of hydrocarbon that we bring in to CO2 and water. Now, you may say to me, but Audrey, you're still generating CO2. But let me share how significant the impact is of converting that methane to CO2. So if I had 5 million standard cubic feet a day that I was venting, I would release about 8,400 tons of CO2 equivalent a day. By cleanly combusting it, I drop that to 260 tons. In other words, I have dropped my greenhouse gas emissions by about 8,000 tons a day. But more importantly, I've done it at a cost of less than 10 cents a ton of CO2 reduced. And this is specifically on operations that we've been doing around pipeline blowdowns and equipment maintenance. Those would typically have been vented because if we were close to a community and because of the high volumes, if we had a flare, we would create a big problem in terms of radiant heat and of course visibility. So by venting it, which has been a common practice, we eliminate some of these problems around heat, but of course we're venting a significant amount of methane.
It reminds me of my time and experience working in Australia, and the LNG plants might be an interesting candidate for this because when, as it turns out, when you're chartering an LNG vessel to take your cargo to market, there is always a residue in the vessel to keep it chilled. And so because you don't want to mix that with the LNG you're about to load into the vessel, you offload it and you flare it. And these flares are gigantic. Like they said, and it was in Darwin, and the column of flame was staggering. And the practice was to do it at night because there would have been black smoke, and you can't see that in the dark, but you can't avoid the scale of this flame.
Right.
It's just an extraordinary sight and very noisy. So just around the world, there's just one example of the potential for revisiting how we deal with the combustion of these molecules so that they are safe. So how does it? So in the combustion chamber, you said there's a vortex. I'm imagining kind of like almost how Dyson's vacuums work. They bring an extraordinary amount of air and create pressures that trap the gases in place so that they can be combusted. It takes energy to do this, I'm guessing. Is it so? How energy intense is it, and what energy source is required to actually do the combustion?
So what we're actually doing is converting our pressure in the gas, and by pressure I don't mean thousands of pounds. It's somewhere between 10 to 20 pounds, and we're converting that pressure to a kinetic velocity. So we're not actually adding a whole bunch of energy, but if we've got some pressure in the gas, that's all we really need. And so this, the testing Shell had done showed that we had the ability to bring in over 150% excess air. And so when we're combusting associated gas, we want to make sure we've got lots of air to complete the combustion process. We're mixing it really well. And because we're creating this vortex, we're leaving that molecule in our chamber for an extended period to make sure it has complete time to finish the combustion process, right? So if I take methane and I have oxygen with a spark, I turn it into 1 molecule of CO2 and 2 molecules of water. That's it.
And some heat.
And some heat.
And heat, yeah.
And we're the first company globally to have received ISO certification, and it's ISO 14034 on our combustion efficiency. So clients, when they use us, can be absolutely comfortable that we are able to do what we say, which is destroy it at 99.99% efficiency.
Yeah, that's a huge number. What is the? What do regulators say when you meet with them and declare? Literally 4 nines, 5 nines, 99.999, but 4 nines, very high efficiency. Yep. What is their reaction? Do they want to see the studies, obviously, but what do they say?
Well, and it was interesting because the first regulator that allowed clients to use our high efficiency in their air quality determinations was Colorado.
Oh,
And at first they said, really? Do
yeah.
some field tests and
Yeah,
help
show me the
prove
money.
us. Exactly. And
Yeah.
so our client did some field tests. And what's quite remarkable about Colorado, within 3 months, they'd given our client approval to use that high efficiency. Now, in the United States, the significance of that is it allowed them to increase their oil production at their pad site.
Oh.
Because in the US, there is a very strict limit on the amount of VOCs you can have coming from a site. And it's capped at 100 tons a year.
Per site.
Per site. And so our high efficiency brought them well under that limit, what's referred to as Title V. And so it allowed them to actually increase oil production. The second regulator that did that was North Dakota.
So this is now in place in 2 U.S. states. This is really important because if you can, get your cap stays in place, your performance that allows you to operate well under the cap by increasing your production, it effectively gets that resource out of the ground faster, converts it to cash quicker, and at the same time is reducing the environmental impact. Like it's, for an operator, it has to be a clear win, because if you're running your facilities below below their productive capacity based on the cap, you have not much option but go drill another well, rather than sort of run the wells that you've got to their theoretical, at a much higher level of productivity. So the economics here must work out very favorably to people who put this technology in place.
Exactly. And in the United States, depending on where you are, that you also have different non-attainment zones, right, where the rules are even tougher, i.e. the air quality doesn't meet the national standard. And they've got different degrees of where it doesn't meet the national standard. So this is a big opportunity. But in addition to the benefit around regulation, there's also a benefit in terms of social license.
Right. Yeah.
Right.
No smoke.
Exactly.
CO2
right.
and water, and maybe you can see some ripples in the sky air from the heat, but no smoke.
Yeah. And so in Colorado, the DJ Basin is actually in the middle of Denver.
Ah, right.
Right. So the community has a lot of say, and they changed their regulations a couple of years ago, very much driven not so much from oil and gas development, but focused on meeting the community needs and keeping the community safe. So Colorado has banned flaring and venting. And they're pushing very much for this concept of clean and closed combustion.
Yeah, makes complete sense. When you think about it, if you spill, you can dig it up and clean it. But once you've put it into the air, it's gone forever. So the tougher rules are going to be on air emissions, it would appear, down track. And are these regulations, are they starting to migrate to other jurisdictions beyond just the United States?
Oh, for sure. So it's migrating, and New Mexico has put out new regulations. So has Pennsylvania. But we're starting to have a lot of conversations globally. So Latin America, the Middle East, Africa. So it's very exciting to see how this conversation is starting to change. And you will have seen the UN and the European Union talk about methane being the low-hanging fruit, right? It's the one thing that we can apply as a lever that we can do quickly, cost effectively to make an impact on this temperature rise. And so for me, I've spent 22 years on this methane journey. It's very, very encouraging, to see how the conversations are starting to change. And Stanford published a paper, and they had published and said the solution to climate change is counterintuitive.
Yeah.
Turning one greenhouse gas to another.
Yeah. Yeah, because of this upfront loading impact, degrades more slowly and has a huge lifetime immediacy of impact in terms of trapping heat. It's really the key. And a couple of other thoughts come to mind as kind of as I sort of mentally consider
Mhm.
this as a possibility. Is there a scale limitation, or is there a scale point where this technology is economic? In other words, if I had
Yeah.
a very low productivity well, at what point does it make sense for me to say, okay, I should really be combusting this, not just venting it.
It always makes sense, right? So we build a wide variety of sizes, you
So
know,
it's very
all the,
small to very large to,
yeah,
yeah.
because it's, over a 20-year period, because methane's 86 times worse than CO2, uh, there's always a benefit if you're focused on climate change and emissions.
Right.
And just making sure that you're combusting it and not putting it into the atmosphere as methane always brings value. And there's an enormous voluntary market starting to evolve. And so we can demonstrate, certainly not at the tiny volumes, but sort of in the mid range, for example, 300 MCF a day flare, right? It's not big by any means. And oftentimes that's a volume that doesn't really support infrastructure.
Yeah.
But by cleanly combusting it and maybe generating about 200 kilowatts of power for the site, you've got an opportunity there to reduce greenhouse gas emissions for almost zero cost.
Mm-hmm.
And if you can use it to offset the liability on your balance sheet, and a lot of companies have an internal price of carbon of $50 a ton, that investment at the end of the day would generate over 100% return on investment.
And as we ramp up our cost of fossil fuel emissions, the taxation rates, just gets
Yeah,
more and more economic every day to just do something with it. Yeah,
exactly.
quite right.
Exactly. Right. And
Mm.
and so I think people are missing, by focusing on carbon, and taking carbon out of the atmosphere, I think people are missing, or have picked the most expensive thing first.
Yeah.
Right. And reality is dealing with carbon will take a lot of dollars. And so that's why, when you look at carbon capture, for example, and I'll pick two examples. In Canada, we've done the project at Quest
Mm-hmm.
and Boundary Dam in Saskatchewan. Both of those projects had a price tag of over $1 billion to sequester 1 million tons of CO2 equivalent a year. Now, remember, I gave you a number earlier that said for $3.6 billion, we could reduce greenhouse gas emissions 2 million tons a day.
Mm-hmm.
Both those projects have spent just a little under $3 billion to achieve in 1 year what that similar investment could do in a day.
In a day, yeah. So 300
And
times improvement if you just spent the money in a different direction.
exactly,
Yeah,
if you focused on methane instead of CO2.
instead of CO2. Yeah, one of
Mhm.
so as you mentioned, the stream coming out of, I'm visualizing a Questor incineration
Mhm.
chamber, and coming out is CO2,
Yeah.
water, and heat. And the what happens? So the water is, it's going to be vapor, I'm assuming.
Mhm.
Is the heat capturable? Is that something that actually has value as well? Because, I'm visualizing heat. There's all kinds of fun things you can do with heat to create value rather than just putting it into the air.
You bet. So we passionately believe, because we're an enclosed chamber, we've got the heat in our chamber. So one of the projects that we've got underway is taking that heat and generating power using an organic Rankine cycle, right? Which is a steam cycle, but because we're using an organic fluid, we're at low pressure and low temperature, and we can handle, all of this low grade waste heat that's not being utilized right now. So it's very much around improving the efficiency, right? Which is the second leg of the stool.
Yeah.
In addition, we're working on technology that allows us to use that heat. So once again, because we're in an enclosed chamber, we can take a slipstream of it
Mm-hmm.
and use it to actually treat produced water. We've got a big issue with water and where to dispose of it after we've finished with it from an industrial process point of view.
Yep.
We know water is going to be our next challenge, and we can see globally there's so many areas where we have drought. We want to keep that water in the ecosystem. So by cleanly combusting, one of our products of combustion, of course, is water. We keep it in the atmosphere. Now, we could remove the heat and condense it for reuse.
Yep.
But we can also use that heat to reduce the volume of water that we have to dispose of. And once again, keep it in the ecosystem. So that's one of the other technologies. Now, we haven't fully commercialized it yet, but we've built a prototype. We filed a patent, and what we're doing there is we're cross-flowing our flue gas from our incinerator or combustion unit with the produced water, so humidifying that flue gas and reducing the volume. And once again, we've taken care of the emissions in that setup.
Yeah, it's brilliant. Sort of becoming more fully circular, which will be incremental benefit. It's been very fascinating to kind of dig into this in a bit of detail, Audrey. If people want to learn more about this whole notion of the circular nature of treating these waste gases and disposing of them in a more creative way, where would they go? What's the website that they might want to visit?
So you can visit us at questortech.com, and I'll spell that.
Yeah,
so
please.
QUESTORTECH.com. We have a chat bot, so you can talk to us directly or send us an email at net zero.
That's
I
brilliant.
look forward, so look forward to connecting and helping everyone get to a path to net zero.
Audrey, thank you very much for coming on Energy Innovations today.
Thank you, Geoffrey, so much for giving me a chance to chat with you and really talk about a very, very important conversation.
Yeah, I appreciate the passion. Thank you again. And this has been an episode of Energy Innovations. Please tune in again in short order for another episode. Bye for now.
Thanks for joining our latest interview on Energy Innovations from EnergyNow Media. Don't forget to hit that like button, subscribe, and share this video. You can contact us at info@energynow.com to book your appearance or to become a sponsor.